Hello everyone, welcome to the YouTube channel of Yourpedia. I am Vineet Sharma, your mechanical mentor here. So as you know, the BEL has announced the vacancies for the BEL Probationary Engineer. Okay, and this time the vacancies are very huge. Around 300 vacancies has been there, and out of which it is comprising of mechanical, electronic branch, civil, CSC branch as well as the electrical branch here. Okay, and for the mechanical there are around 109 vacancies, and the maximum age limit for this particular exam is 25 years. Okay, so I've already explained you each and everything, that what is the exam pattern here, what is the previous paper analysis here, and how many questions has been asked from which topic. Now in this particular video, what I am going to do here, I am going to solve some previous questions of the heat transfer subjects, comprising of 20323 as well as the 2025 year. Okay, now I have already told you that this particular subject is comprising of around 10% of the entire exam. Okay, and the questions are very simple, there is no issue. Okay, just the theoretical question has been asked, so there is no need to do the numericals here. Okay, if you have a just basic understanding of each and everything, you can also solve the easy numericals here. Okay, as you know, in this exam there are total 125 questions, and you have to solve those 125 questions in the 120 minutes here. So the time is around 1 minute for each and every question. Okay, na? So you can expect all the theoretical questions this time also. Now in this case, if you just see, so this is all the information which has already been shared with you. Okay, now so we have already seen this. The Vijayender has already been explained this to all of you. So we already have started the modules here, and this module has been specifically the no notes making here. In this case, you don't have to make the entire notes here. Okay, you just have to revise the PDF which we are going to provide to you. Okay, and the daily live classes are going to be conducted here. Okay, the theory of machine has been started right now. Okay, now, and the next thing is, in this case, if you just see, so this is a 2-month module here, in which we are going to cover up the entire theoretical portion, as well as we are going to provide you the practice questions also. So just make ensure that you started your preparation very well on the time here. And this is the previous year analysis. So here you can see all the subject analysis has been done for the 2023 exam as well as the 2025 exam also. Okay, and out of this, if you just observe the heat transfer subject, it has asked the 9 question has been asked from the heat transfer in 2023, and 5 question has been asked this time from the heat transfer subject here. So I can say on an average 10% weightage has been given to this particular subject here. Okay, don't think that this is a not important subject here. This is a very important subject for you as well. Okay, now it is comprising of thermal part also. Now in this case, if you just see what kind of question has been asked here, so let us start with the questions. So first of all, just see, this is a very simple question which has been asked from this particular subject. Now in this case, if we just observe very carefully, what is the question? Which one of the following is an example of convective heat transfer coefficient? Convective heat transfer they have asked. Okay, so in order to solve this question, you have to first have to have an understanding of the convection part, conduction part, as well as the radiation mode of heat transfer. If you know the proper definition, if you know the physical significance, okay, and how the heat is transferring in all the mode of heat transfer, you can simply answer the question here. It is not a direct based question here, although if you just see, because they have provided the options in such a way, they are basically some practical based phenomena. Okay, and you have to mark the answer as per your observations. So let us start with the first option. So you are going to see in the first question what is given to us: heating a metal rod. Okay, now if you just observe very carefully, in the heat transfer we have 3 mode of heat transfer. The first one is a conduction. Conduction is basically done in the it is predominant in the solid bodies. Okay, even though it is applicable, it is also conducting in the liquid as well as the gases here, but its effect is not so much significant as compared to the convection part. Okay, so generally the conduction mode of heat transfer is generally studied for the solid bodies, and in this case the heat is transferring by means of the free electron transfers as well as the lattice vibrations here. Okay, so if you observe this, in this case what is given to us: heating a metal rod. Is it an example of convective heat transfer or not? You have to mark. So as you can see, in the case of convective heat transfer, what is the required condition? The required condition is that the heat has to be transferred from the solid body to the fluid here, or from the fluid to the solid body here. Okay, or I can say due to the bulk motion of the fluid, the heat has to be transferred here. But in the case of heating a metal rod, there is no bulk motion of the fluid here. The heat is transferring from one part of the metal to the another part of metal with respect to the free electron transfer or the lattice vibrations here. This mode of heat transfer is not involving any type of the, I can say, the motion of the fluid particles here. So it is not an example of a convective heat transfer coefficient. Okay, this is entirely example of a I can say conduction mode of heat transfer here. Okay na? So you can simply skip the option number A here. Now coming back to the second part, sunlight warming the earth here. So just see, sunlight which is coming out from the sun, okay, it is coming in the form of electromagnetic waves here. It is coming in the form of radiations here. So I can say the warm feeling of the earth which has been observed there due to the sunlight, it is due to the radiation mode of heat transfer. Why? Because in the case of radiation mode of heat transfer, it does not require any the heat does not require any type of medium here in order to propagate from one part to the another part here. Okay, so this is the general phenomena which is comprising of radiation heat transfer. And in this case, if you just observe very carefully, in the case of radiation, here we have one theory which is known as the Prevost theory. Okay, and if you just see, Prevost theory basically tells you that if a body is having a temperature more than 0 Kelvin, in that case what is going to be happen there? In that case, all the body is going to radiate some amount of energy here. Okay, it is going to propagate the different type of radiations of different wavelengths here. Okay now, and in this case, so here you can see in this option number B, it is entirely an example of a radiation heat transfer here which does not involve any medium. Next part, boiling water. In the case of boiling water, from the name itself you can say, I can say the heat transfer is going to be predominant by the convection only. Why? Because in the case of boiling water, there is a continuous random motions of the atoms and molecules or fluid particles which has been taking the heat from the heated surface due to the bulk motion here. Okay, so that is a simple question here. Okay, and it is a practical example of a convective heat transfer here. Now coming back to the last part, heat dissipated by a transfer. Now what is that here? So in the case of a transformer here, first of all, what is there? The heat transfer is basically I can say it is this phenomena is taking place of the two phenomena here. Okay, it is taking place due to the two phenomena, either due to the convection part or either due to the radiation part here. Why? Because in the case of transformer, the temperature of the transformer is going to be very high as compared to the surrounding body. So now if the temperature is very high as per to the surrounding, then what will happen? The radiation mode of heat transfer is going to be taken place. Generally, if you just see, in the case of radiation mode of heat transfer, we have a Stephen-Boltzmann law, okay, which basically tells you that the energy emitted from the surface is directly proportional to the sigma T to the power 4 here. So higher the temperature difference, higher will be the radiation heat transfer taking place from the body. Okay, so I can say in the case of a transformer, the heat which is being radiating from the transformer, it is due to the radiation only, due to the high temperature. Along with that, if you observe very carefully, the atmospheric air is present everywhere. Okay, so I can say the the heat transfer is also taking place due to the convection. Okay, so basically there are two modes of heat transfer which are simultaneously occurring in the case of a transformer here, the radiation part, along with that the convection part here. Okay, so in this question we have to specifically mark the answer in which the convective is taking place and not the radiation part. So I can say the option number C will be the exact answer here. Okay, so that's a very simple case. Now coming back to the next question here. So this is the entire, here you can see this is the entire explanation here, you can go through that. Okay, so this is a very simple case. Coming back to the next question. Okay, next question is related to the convection heat transfer. Okay, in this question they have asked you, the Prandtl number is crucial in understanding the relative growth of the hydrodynamic and the thermal boundary layers. When the Prandtl number is more than 1, which of the following statement is true? Option number A is hydrodynamic boundary layer grow faster than the thermal boundary layer. Thermal boundary layer grows faster than the hydrodynamic boundary layer. Third, the growth rate of the boundary layers are unrelated to each other. Okay, and the option number D is both the boundary layers grows at the same rate. So just see, just right now what I have told you. First of all, this question is related to the convection heat transfer. Convection is a mode of heat transfer which is taking place between the bulk motion of the fluid as well as the solid body here. Okay, so in this case the temperature difference has to be there in between the solid fluid as well as the body here. Now in this case, we just observe whenever a liquid is flowing over a solid body, whenever a liquid is flowing over a solid body, what will happen? So if there is no temperature difference here, there will be a formation of a hydrodynamic boundary layer. So hydrodynamic boundary layer is forming due to the viscous effect here. Okay, why it is forming due to the viscous effect? Because as soon as the fluid comes into contact with the solid surface, what will happen? A boundary due to the no slip condition, the fluid layer will stick to the solid surface here. So you are going to see that we have a formation of a stagnant layer over the solid surface. Okay, now over to this, what is going to happen? All the layers are going to be restricted by the movement here. Okay, due to the viscous effect. So now you can see the stagnant layer which is formed over the solid surface, it is going to restrict the movement of the top layers here. Okay, so due to which a velocity gradient is going to be formed. So we can say there will be a formation of a hydrodynamic boundary layer. Okay, and due to the hydrodynamic boundary layer, what is happening? There is a velocity gradient present normal to the surface here. Okay, so this is a important part. Now along with that, just suppose that there is a temperature difference also. In the first, I have told you that there is no temperature difference. So now let us say there is a temperature difference associated between the solid surface and the fluid here. Then what will happen? If the temperature difference is there between the solid surface and the fluid, then the formation of a thermal boundary layer will take place. The formation of a thermal boundary layer will take place here. Formation of a thermal boundary layer will take place. Okay, just remember that part. So here you can see, let us say this blue color is representing the thermal boundary layer. Now the thermal boundary layer is a region in which the temperature gradient can be observed. For example, let us suppose the surface temperature is equal to 100 degrees Celsius. I am assuming a random data, and here we have a fluid which is having a temperature of 30 degrees Celsius, let us say. Okay, now if you just observe the very carefully, due to the no slip condition, the layer has been stagnant close to the solid surface. So this stagnant layer is going to attain a same properties, they are going to attain a same temperature as per the solid body here. But if we just see, the layers above the stagnant layer are going to experience a change in temperature. Okay, the layer which is very close to the stagnant layer, it is having a higher temperature, but the layer which is at a higher distance, they are going to have a lower temperature. Okay, so you will observe that in the normal direction, same like the velocity gradient, we are also going to observe the temperature gradient here. Okay, now so due to which the thermal boundary layer is going to be formed. Now here in this case, we have a Prandtl number. Now what is the meaning of Prandtl number here? Prandtl number is a very important number. Okay, it is a dimensionless number which basically compare the thermal boundary layer with the hydrodynamic boundary layer. Okay, just remember that part. Now in this case, you have to understand, first of all, here the Prandtl number mathematically is defined as the ratio of the kinematic viscosity to the thermal diffusivity. Okay, it is defined as the ratio of the kinematic viscosity to the thermal diffusivity here. So what does the physical significance of kinematic viscosity? It tells you about the momentum diffusion rate which is taking place through the boundary layer, so the hydrodynamic boundary layer. Whereas alpha is the thermal diffusivity which tells you about the I can say thermal diffusion rate across the thermal boundary layer. Okay, now so I can say that Prandtl number is basically comparing the relative thicknesses of the hydrodynamic boundary layer, this green one here, and correspondingly the thermal boundary layer. Okay, so that is important for you. So I can say the Prandtl number is around del by delta t. It is directly proportional to the del by delta t to the power cube here. Okay, just remember this part here. This is very important for you. Okay, so now you can see it is basically comparing the relative strength of the hydrodynamic boundary layer to the laminar to the thermal boundary layer here. It is defined as a ratio. It is basically also comparing the momentum diffusion rate to the thermal diffusion rate here. Okay, so now on the basis of the value of the Prandtl number, we may have a different conclusions. For example, if you observe, when the Prandtl number is more than 1, when the Prandtl number is more than 1, then what will happen? The value of the delta is going to be more than delta t. Okay, what is delta t here? Delta t is representing the thermal boundary layer. Delta t is representing the thermal boundary layer here. Okay, na? And corresponding delta is representing the hydrodynamic boundary layer. So I can say in the case of a Prandtl number more than 1, the corresponding thickness of the thermal boundary layer, hydrodynamic boundary layer is going to be more than the thermal boundary layer here. Okay, now so that is the important part. So now the next part is when the value of the Prandtl number is equal to 1. In that case, the value of the delta and the delta T will become equal to will become same here. So once these two value will become same, so I can say the boundary layers are going to be remain same here. Okay, the thicknesses are going to be remain same. Okay, next part, when the value of the Prandtl number is less than 1. So can I say that when the value of the Prandtl number is less than 1, in that case the value of the delta is going to be more less than the delta T. Okay, so these are some of the conclusions which we can draw from the relative values of the Prandtl number. So that is a very important part here. So I can say in this case Prandtl number is more than 1, so the hydrodynamic boundary layer grows faster than the thermal boundary layer. That is the important part here. Okay, I hope it is very clear to all of you. So it's a very simple part, even though you required you have to just a basic understanding of the boundary layer here, along with that the convection heat transfer, that's it. So here you can see everything is mentioned here. Okay, so you can go through that. So Prandtl number is a dimensionless number here, which is also considered as a property of the fluid. Okay, which basically compares the momentum diffusivity to the thermal diffusivity. Momentum diffusivity means momentum diffusion rate, that is kinematic viscosity. Thermal diffusivity means thermal diffusion rate, that is thermal diffusivity here. Okay, na? Okay, so the next part is, so similarly this is the explanation for all the parts here. So here you can see in the case of Prandtl number 1, what is a practical example here? For the Prandtl number 1, the practical example is for the engine oil or the glycerine. Okay, the thermal boundary layer is thin as compared to the hydrodynamic boundary layer. Why? Because the value of the kinematic viscosity for the engine oil or the glycerine is more than the thermal diffusivity here, due to which the thermal boundary layer is going to have a smaller thickness here. And in the case of a Prandtl number less than 1, Prandtl number less than 1 here, Prandtl number less than 1. Okay, just give me a second. Prandtl number less than 1 here. What is the practical example here? In the liquid metals. In the liquid metals such as mercury, the heat spread more rapidly here. Okay, because in that case the kinematic viscosity is less as compared to the thermal diffusivity here. So the thermal diffusion rate is going to be far much higher as compared to the momentum diffusion rate here. Okay, and similarly you can see the remaining options also. Now let us move toward the next part, third question. In the third question, it has been given the Rayleigh number in the free convection scenario is essential to predict the onset of a turbulence. Which of the following dimensionless group is represented by the Rayleigh number? Okay, so here again this question has been came from the convection part and specifically from the free convection. Okay, if you just see in the last question we have seen the concept of a Prandtl number, that is I can say it is common to the free convection as well as the forced convection here. But in this case this question has been specifically asked from the free convection. So actually what happens when we study the convection part, there are two type of convection. Either we have a free or natural convection, or either we have a forced convection here. Okay, so either you are going to see free convection, which is also known as natural convection here, free convection as well as the natural convection, or you can see we are having the forced convection here. Okay, so in order to quantify the free convection as well as the forced convection, again we have a Newton law of cooling, which is basically given by Q is equal to HA delta T. So you have to understand the value of the heat transfer coefficient is defined in different ways in the case of free convection as well as the forced convection here. Okay, so when we talk about the free convection, in that case the heat transfer coefficient is basically depending upon the gravity, temperature difference, isobaric thermal expansion, viscosity, okay, thermal conductivity, density, like this parameter here. In the case of forced convection, it is also depending upon the velocity. Okay, now so actually what happens, what are the example of forced convection? So whenever the fluid is flowing over a, I can say, heated surface or a cold surface, but due to and the flow is taking place due to the external agencies like external pumps or any external machines. In that case, it is a case of a forced convection. Okay, for example, the radiator of an automobile, the heat exchangers, boilers, all of those are the example of a forced convection. But when we talk about the free convection, in that case the fluid is flowing over a hot surface or a cold surface due to its own. Okay, you are not providing any external power, external energy into the fluid in order to transmit the, I can say, in order to take away the heat here. Okay, the fluid is flowing due to the density difference on its own here. Okay, thus you have to remember that. Now in this case, when we quantify the when we study the free convection, so the important dimensionless number are Nusselt number. First of all, okay, we say that the Nusselt number is a function of Grashof number and the Prandtl number. We say it like that here. So in this case, the Nusselt number is basically a number which is comparing the convection mode of heat transfer with the conduction mode of heat transfer here. Okay, it tells you that how the flow and I can say how the heat transfer has been enhanced due to the convection over the conduction in the liquid here. Okay, that is the significance of Nusselt number. But when we talk about a Grashof number tells you about the I can say the strength of a free convection here. Okay, now Prandtl number we have already seen, it compares the boundary layers here. So that's a simple case. Now in the case of a forced convection, we see again the Nusselt number is basically a function of Reynolds number and the Prandtl number here. Reynolds number and the Prandtl number. So generally the Reynolds number is used here because in this case the flow is taking place due to the external agency. Okay, you are providing the energy into the fluid, and due to that energy, what is happening, the fluid is forcefully flowing over the heated surface or a cold surface, or it is picking up the heat from the solid surface or supplying the heat into the cold surface here. Okay, now so generally the forced convection is more, I can say, dominant as compared to the free convection in transferring the heat here. Why? Because the value of the heat transfer coefficient is generally far higher as compared to the free convection here. Okay, now so if you compare the value of the air, or if you compare the value of the any gases, specifically the heat transfer coefficient values here. Okay, so generally the forced convection values are higher as compared to the liquid here. Okay, now so just remember that part. So that is a very simple case. Now here we have one number which is known as the Rayleigh number. Now what is the meaning of Rayleigh number here? So Rayleigh number is basically related to the free convection part here. Okay, it is related to the free convection part. Again, it is a dimensionless group. Now how do we define it? Okay, just see one more thing. Whenever you are doing the study of a free convection, okay, we have to check that whether the flow is laminar or turbulent. And similarly, whenever you are doing the study of the convection, forced convection, there also you have to check that whether the flow is laminar or turbulent here. Okay, so in the case of a forced convection, we don't have to take so much worry here, because there we can define the laminar or turbulence depending upon the value of the Reynolds number. How? If you just if you have a basic understanding of fluid mechanics, so there you will have read maybe that whenever the fluid is flowing, the value of the Reynolds number is less than 2300. When the value of the Reynolds number is less than 2300, at that point of time you are going to observe the flow as a laminar flow. Okay, and when the value of the Reynolds number is greater than 4000, then we have a turbulent flow. That is a simple thing which we covered in the fluid mechanics, okay, for the flow through pipe condition. And similarly, if you are studying the forced convection for the flow over a flat plate, in that case we have a value of Reynolds number less than 5 lakh to characterize the flow as laminar flow here. Okay, and similarly, when the value of Reynolds number is more than 5 lakh, then we have a turbulent flow. Just remember this one. But now when we study the free convection here, okay, but when we study the free convection, in order to find out that whether the flow is laminar or turbulent, here we define a Rayleigh number. Okay, so on the basis of a Rayleigh number, you characterize the flow as a laminar or a turbulent here. Remember that part, that is very, very important for you. Okay, because in some over the internet here, some sources it is mentioned that the laminar and turbulent flow has been characterized on the basis of Grashof number. That is a completely wrong information here. Okay, now on the basis of Rayleigh number you characterize that whether the flow is laminar or a turbulent here. Now in this case, when the value of the Rayleigh number is less than 10 to the power 9, we say it is a case of a laminar flow. It is a case of a laminar flow. And when the value is more than 10 to the power 9 here, we have a flow as a turbulent flow. Okay, now so this is how you characterize the flow. Now what is the meaning of, what is the definition of Rayleigh number here? So generally the Rayleigh number is defined as the product of Grashof number multiplied by the Prandtl number. That is how you define the Rayleigh number here. Okay, so if you just see the question, this question here, in that question they have directly asked that what is the meaning of Rayleigh number here. Okay, so here in this case I can say it is defined as the product of Grashof number and the Prandtl number, and it is essential to predict the flow as laminar or a turbulency here. Okay, na? And what is the value here? The value is 10 to the power 9. Less than 10 to the power 9 laminar, more than 10 to the power 9 turbulent here. Okay, so that's a very simple case. So here you can see option number 1A we have seen here. Okay, coming back to the option number 2, ratio of the conduction to convection here, that is a completely wrong statement here. Here you can see the flow which is taking place, the flow in the liquids or a gases here, it is taking place due to the convection here. Okay, and so I can say there is a number, dimensionless number, which is known as the Nusselt number. It is basically defined as the ratio of the convective heat transfer which is taking place through the fluid to the conduction heat transfer here, which is taking place through the same fluid here, or I can say the conduction resistance to the convection resistance. So the Nusselt number is telling you that how much the flow has been enhancement has been taken place, or the heat transfer has been enhanced due to the convection over the conduction in the liquid here. Okay, now so that is a completely wrong statement here. Third option, product of Reynolds and Prandtl number, that is again a wrong one here. Okay, there is a wrong statement here. The product of Reynolds and Prandtl number, it is used basically in the I can say Reynolds analogy here. Okay, in the analogies here you have used this number here which is known as the Packard number. So Packard number is defined as the product of Reynolds and Prandtl number here. So this number is find its usefulness in the forced convection. Okay, not the free convection here. Now coming back to the next part, rate of advection to the diffusion here. Yeah, so basically I can say it is partially correct, but this is not a exact definition of a Prandtl number here. Okay, now just remember that part here. So this is how you can see that the Rayleigh number is basically the product of Grashof and Prandtl number here. So that's a very simple question here. So I can say the question which has been asked in the BEL exam, they are very simple here, although you can see here this type of question has been asked. Okay, now so you can just see the each and every detailed analysis of the options here, what are their what is the exact answers and why the other options are wrong here. So that is very simple case. Now similarly, so that's it here. Okay, so these are some of the questions which has been asked in the 2023 exam here and 2025 question here. I haven't covered the entire question series here. Okay, now so this is the few questions which have been covered here, and you can see the questions are very simple. Okay, so you have to just make ensure that you start your preparation by keeping in mind that you have to focus only on the theoretical subject, and you have to make ensure just read it very carefully. Okay, you should have a proper understanding of each and every topic here, because a question has not been asked directly here. Okay, for example, in this case they can frame you the question in this way: the Rayleigh number which is defined as the product of Grashof and Prandtl number here, what does it for which purpose we use this number here. Okay, so it is basically used to predict the onset of a turbulence here. So question can be framed in different ways here. Okay, now next, so these are some of the practice questions here. You can just practice on its own here. Okay, for example, for a semi-infinite solid subjected to a sudden change in surface temperature, thermal penetration depth is proportional to, they have asked you. Now just see, I am covering this first question here, that is a very simple case. They have asked you the thermal penetration depth here. Okay, now you have to understand that in the entire heat transfer, which dimensionless number is basically used to I can say to study the thermal penetration depth here. Okay, so there we have a Fourier number. Okay, Fourier number is a number which is used to predict the thermal penetration effect in a solid body. Okay, so if you have a basic understanding of the Fourier number, Biot number, I can say Rayleigh number, Packard number, Nusselt number, okay, Grashof number, and their physical significance, you can mark this mark the answer very easily. Okay, so this type of understanding, it is required in all the subjects of the mechanical engineering. Okay, now, so these are some of the questions, you can go through that they are very simple. Okay, so just making sure that you cover that portion very well. Okay, so this is something which I want to share with you. So thank you very much. And there is one more thing, the dedicated WhatsApp group has been made here for the WhatsApp for the BEL group here. Okay, BEL students here. Along with that, the Google description form has been attached in the Google form has been attached in the description box. Okay, so you can fill that form if you have any query related to the BEL. Okay, so start your preparation. So thank you very much.